So just keep going. I'll get started.
Yeah.
Yeah. Morning, everyone. So I have to start this lecture backtracking on all the bollocks I taught you yesterday. There was a number of mistakes. The people came up afterwards and corrected me. Thank you for that. I'm going to. They're not such bad mistakes, but I should certainly point them out. And I've got a list somewhere. Okay, so the first one is, if I can find it, here we are. I wasn't consistent in the in partial derivatives. Okay, now somebody pointed out that this Maxwell's equation was with partial derivatives, and that conventionally Maxwell's equations are partials. All right, and in the derivation of the Maxwell's equations, I used standard derivatives. So to be consistent with Maxwell's equations, it actually makes no difference. Of course, when I apply Stokes' theorem here, all I'm saying is that the derivative d by dt of b dot dA, I hold a constant, the area constant, in this formalism. So I'm going to, just to be consistent, going with a partial derivative there. So it just there and there. That's the first thing. Somebody spotted that. Good spotting. Right. The second thing is there was a sign missing here, a minus sign. So if you could correct that. This was Faraday's law in integral form. There was a sign missing there. Okay. And finally, this is the big one. Now, I was always a little bit worried about a sign I told you about here. I could never really quite convince myself that sign was correct. And I convinced myself it wasn't correct. I told you that because of this going anti-clockwise, it was I picked up a minus sign. That was just totally wrong. I mean, I did all the coordinates, and that sense goes actually in the correct direction for a right-handed system. So that was wrong. Now, in going into this in depth, I tried to find the origin of this missing minus sign, and it's a fudge actually. It's a fudge because it depends entirely on the sign that you take dA in the calculation of the flux. So I can take when I calculate the flux, I can take dA going into the page or coming out of the page. And the question is, which one is it? Well, unfortunately, in this particular case, it's totally undefined because the method is dodgy, right? And it's this method of using for the homopolar generator, Faraday's law, is standard in textbooks, but it is a dodgy method. And I keep it in here because, I might take it out for next year. But the point is that this method of flux linkage works for the area inside a circuital loop. Okay, so if you've got, which I'm going to do next, if you've got a wire which is rotating in a magnetic field, or a wire that's being pulled out of a magnetic field, then this loop can take a current. And there the A is inside that loop. And in that case, A, the vector area A, is conventionally defined as with a right-handed screw. All right, so if that is the direction of the current, A points out according to the screw rule. All right, and that gives you the correct, that gets you the right sign in Faraday's law. Okay, where the current opposes the field that causes it. Okay, so that's the area A. In this case, however, the current is all the way over this generator, over this disk. It radiates outwards radially. So there's no corresponding loop, so there's no area to define, okay, for the vector dA. So if you want to read more, it's in Griffiths. You know, it's the recommended textbook, and Griffiths actually spends a page on this. I hadn't realized only when I tried to work out what was going on. So it's strictly speaking, I'll read it out. This method from Faraday's law is not entirely sensible, since the current is continuous across the disk, and the integral of the flux is in principle only applicable for a surface bounded by a closed current path. So it's in there. But having said that, the method works. It's just a little bit of a dodgy method in this particular case for using the flux. This method for using the Lorentz force, however, is completely valid. Okay, where one has a force due to a motion V in a field B, and you have a force V cross B. So this is completely valid. That gives you the value of the EMF induced, which is across this from the center to the outside. Right. And I hesitate on saying this because this is a point of confusion, the sense of the voltage and the EMF. The voltage and EMF actually pointing in different directions. This is like a battery. If you think of a battery in a circuit, the direction of the conventional current is actually going from minus to plus. All right, now think about that. And that's the origin of the sign, in Faraday's law. You're going from minus to plus, which is like not quite intuitive. All right, so if you've got a closed circuit loop, then the total potential around that loop has to be zero. So it's exactly like in a battery. In a battery, the conventional current inside the battery goes from minus to plus. All right, and again, think about that. The EMF is like a generating this field, and hence the flow of current. All right. Now, I hope that didn't confuse the hell out of you, but these revised notes are on the web, where I just put in this health warning, and I also confess to the sign problem. Right. Good. So now we'll go to something completely fine, which is the rotating, an example of a coil rotating in a B field. Right. So the coil rotating in a B field. I'll write this on the board. So the coil has n turns. That just means the wire is wrapped around itself n times. rotating at an angular frequency omega in a uniform B field. Right, and it's going round and round. This is a poor picture, of course, but it's sort of like going around like that. So it's rotating in this B field, which is going into the board. Right, now looking from the from the direction, here is the B, so you're looking in this in the plane perpendicular to the board here, into the screen. Then this here is the coil, and it's rotating round and round like as shown in a circle. Right, so it's in this plane it's doing that. Right, so what you've got here is movement of the coil in a uniform magnetic field. So this problem is completely geared up to this method using the magnetic flux. So I can write down the magnetic flux. Right, so the magnetic flux phi is, remember, it's the integral of the field over the area. So it's the integral B dot dA over this surface here enclosed by the loop, which of course equals B times A n sine theta. Now, okay, so there's the diagram. I hope you can see. Here's B. Theta is, how do I label it, is like that. A comes out in that direction. So this here is 90 minus theta. So when I do the dot product of the area A, sorry, I'll put that little dA with B, I get a sine theta term from the dot product. And this is, the n here is because since each turn of the coil links the flux. Right. So that's the magnetic flux. So now I can calculate the EMF induced. And the EMF induced is just appears across here. Right, so the positive and the negative charges will migrate to the ends due to the electromagnetic, due to the force, the Lorentz force. So this is d minus d phi by dt. So I just differentiate this. Minus NAB omega cosine omega t. Right. So what I didn't write here was where theta is equal to omega t. Right. So I hope that's clear. So the angle theta here is just equal to angular frequency times time. So when I differentiate this with respect to time, I pick up a cosine from the differential of the sine and a minus sign. Right. The minus sign is from there, actually. Right, so this is the principle of a generator, dynamo, So this principle is incorporated in terms of most aspects of electrical power generation. Right. And so it's just an example of induction. Right. So in the problem sets, there's all sorts of different examples for you to work on. Good. And so now coming to lecture 16, I now come to self and mutual inductance. And this is where the electromagnetism course sort of meets the circuit theory course. And I hope by the time I've finished this lecture, I hope you understand what an inductor is in an electrical circuit. And I'm going to talk about what is self-inductance. Then I'm going to calculate the self-inductance of a number of things, right? A long coil, and then I'm going to then take this coil into a resistive load, where you'll see the analogies with circuit theory. Self-inductions of a coaxial cable, two parallel wires, and then I'll probably run out of time, and I'll get to, in the next lecture, mutual inductance, and calculate the mutual inductance of a pair of solenoids. Good. So self-inductance, what is it? I mean, we've set the scene here with the magnetic flux and the concept of inducing EMFs in circuits. Right, so I hope you're sort of happy now that if you take some sort of closed loop circuit like this here, so if you flow current through that circuit, you know that circuit will give you a magnetic field. All right, now it's some weird shape, you don't know what exact form that field will be, but it will, if it's a loop, it will form a magnetic dipole, which will mean that the field comes out either end, basically. And then meets up with itself, because there are no open field lines, they're all closed. Right, and I hope that from what we've done, you can see, I mean, I haven't derived it for every single geometry, obviously, but, you know, I hope you can see that the magnetic field is always proportional to the current. Well, that just comes from the Biot-Savart law. Right, so the magnetic field is proportional to the current. Right, so now if you change the current in the circuit, you'll have a changing B field in the loop. And if you've got a changing B field in the loop, you know that you're going to induce an EMF. Right, so this is following on from that. So Faraday. So we've got a changing B field in the loop. So the changing magnetic flux which phi induces an EMF. Which is like a voltage in the loop itself. Right, so this is the key point. Right, so what happens is you change the current, you change the magnetic field. That changing magnetic field then induces this voltage back in itself. All right? And so the changing magnetic field you've produced links with the coil, gives you an EMF, and that EMF acts to reduce the current in the coil, according to Lenz's law. Right, do you get that? So this is the key of, this is what Lenz's law means. So if you induce this magnetic field, that feeds back into the circuit, which acts to generate an EMF, which reduces the current that caused the field in the first place. Right, and if it didn't, if it increased the current, the current would just take off to infinity, right? It would. So it has to reduce it, all right? And then because otherwise you'd have, infinite energy given off eventually, all right? So that's Lenz's law. So I'm going to write this down, minus d phi by dt. So phi is the integral of is just the integral of the B field over this area. Right, so this is an arbitrary area here. So, and I'm going to write down what I've just said. So that's Faraday's law. So Lenz, the EMF will act in a direction so as to oppose the change in flux. Which caused it. So what this means is that this, like coil, presents a resistance to any changing current, because this field, right, I'll say it again, it induces an EMF, a back EMF, which reduces the current. So it poses an impedance. So I think I'm just writing this down again. EMF induced equals d phi by dt. And there's a minus sign there. And note that it's all linear. Phi is proportional to B, which is proportional to I. So everything is linear. All right, so, and this means that, what I'm going to do is I'm going to define the self-inductance. Now, this is just a definition. Okay, and you'll recognize the symbol L equals phi over I. Right, so L is this standard inductance that you use in circuit theory. Right. And, right, since phi is proportional to I, this is often written, all right, although this is totally linear, that's the definition. You'll also see this written as such, can also be written as L is d phi by di. So it's just a change in phi over a change in I. So I hope that's obvious. If you have a change in that in the flux and a change in the current, which equals d phi by dt over di by dt, just loosely cancelling dt's, which equals minus epsilon over di by dt. So this means epsilon, the EMF is minus L di by dt. Now, that should look completely familiar, right? It's it's like in circuit theory, V is L di by dt. Right, it's equivalent, but you've got this sign difference, and that's, I hope that I've explained that sign. It's because the EMF is opposed. There's a sign difference between the EMF and the voltage, and the EMF. This says the EMF is acting in a sense as to oppose the current that caused it. All right, and if that wasn't there, the current would just blow up to infinity. So the voltage. So if you've got this this coil, you have an EMF which is acting in the opposite sense, and the voltage build-up is across the inductor, so as to act as an impedance to the current. Lenz's law. Right, so it impedes the current that caused it. Right. Okay. So that's it. So that's where, when you did circuit theory, and you probably got hit with this funny symbol that if you hadn't seen it before, and you were told that, then this is where it comes from. Right. So I'm now going to go into calculations of self-inductance. And it actually brings everything that we've done on magnetism, sort of, well, not everything, but quite a lot of what we've done together. So I'm calculating the self-inductance of a long coil like that. Now, from Ampere's law, I'm probably going to have to derive this quickly, just to remind you. Always dangerous, just in case I forget how to do it. But you've got a coil, and you remember you take this Amperian path. This goes off to infinity. That leg there. So we've got a line integral b dot dl is equal to I times mu naught, and those are vectors. So we integrate b dot dl. Those cancel. Besides, there's no field outside this coil anyway if it's very long. That's off to infinity, and the only bit that contributes is that leg in the line integral. So I can write down B is mu naught n over L times I, where n over L is the number of turns per unit length. Right. So I've missed a step there, but if I take this as L or X or something, then this line integral is just B times X. Sorry, I know I'm going to get into a muddle here, but B is I over X mu naught, and then what's how? So, but there are n turns. Sorry, I've got to put n in here. Look, ignore that. I'm ad-libbing here, so I thought I'd better derive it just to satisfy you in case you've forgotten. But that's the source of this of this of the field. So that's the field that I derived a few lectures ago. So the magnetic flux. Okay, so where is the magnetic flux? So if this field is changing due to a changing current here, then the field lines are going like this, right? They are depending on the direction of the current. The field lines are going along there, which means that the flux linked is an area perpendicular to those field lines. All right. So the magnetic flux phi is the integral of B times the area A, which equals NAB. Right. So AB, I think you'll be happy with. This is the area. This is the field. Now this term here, I've introduced. I've thrown this in. All right, because there's a value of n here, because every single turn, if I have a changing field, changing flux, every single turn of this coil links it. So I have the total flux is n times the B dot dA, because every single turn of the coil feels that linking flux. Right. Every turn of the coil of the N coils, I should say, links its own flux. Right. So that's it. So from here, I can write phi is NAB, which equals mu naught n squared. I'm just substituting for B over L A times I. Right, that's phi. And so now L, the self-inductance, is phi over I. So L equals mu naught n squared A times divided by the length L. So that is the self-inductance of a solenoid. Of long solenoid. Right, now so there is that's the self-inductance, so we can go from there to get the back EMF induced in the coil. Back EMF induced is minus d phi by dt equals, so I'll just, somewhere up there at the top, I calculated phi mu naught n squared over L A di by dt, which equals, it's a minus sign there, minus L di by dt. So that's the EMF. That's and it acts in the opposite sense to the voltage that's generated across the inductor. You know, the analogy with circuit theory. Good. Right. So I'm going to follow through this analogy with circuit theory now. So we've got this long coil, area A, length L with n turns, which I where I derive the self-inductance of it. So the coil is now immersed, if that's the right word, in an axial time-varying magnetic field. So I'm going to bung this. It's just an example. So I'm going to bung it into a field which varies like cosine omega t. And of course, the time-varying field, if you've got a time-varying field, you're varying the flux. You know, integral B dot dA is varying, which means you induce an EMF. So here we've got a time-varying field. It's slightly different from the examples we've had before, where we have motion before. This time we're varying the field. It's exactly the same thing. We induce an EMF in the coil, right? So an EMF is induced here. But at this time, we've actually got a resistor here. So I've got a resistor in the circuit. So we've induced an EMF. Now, what happens to that EMF? Because we have this EMF, we will have a current flow because we've got a circuit. Now, as an aside, right? What happens, right? A current flows in the circuit, and that current has the sense to, i.e. the direction, such as the field that it induces as it, you've got a current in a coil which will itself induce a field. That field opposes the magnetic field that caused it changes. So it will have an effect to try and reduce the field that's changing. That's Lenz's law. So anyway, that's an aside. So, but the EMF induced here, gosh, I don't know how many times I've written down that particular equation, is minus d by dt Na B naught cosine omega t. All right, because this is the field, this is the area, and this is the number of turns. Because each turn will generate a magnetic field. Sorry, each turn will link the flux. Okay. It comes in twice, right? The field, the number of turns go into the field because each turn generates the field, and it comes in again in the flux because each turn links the flux. So it comes in as n squared. Right. So Sorry, this is a different problem, right? It doesn't come in n squared. Oh, God. Sorry, it doesn't come in n squared in this problem. B is an external field that's changing. So it's not relating to the circuit in this case, right? So but there are n turns which link this changing flux, and the field is just an external field. It's not. That field isn't generated by the coil itself. So the EMF, just so I just differentiate it, Na omega B naught sine omega t. Right. So that is the EMF, and it's what it is, right? In this example. Now we've got this resistor in the circuit here. So current is going to flow because we've generated a EMF, which is a voltage. So current will flow, and we do an equivalent circuit. Now, of course, the EMF is generated, within this coil. It's it's generated effectively along the length of the coil. But we can actually take it outside the coil, have this as a sort of a resistive element, an element of impedance, and we can take the EMF outside as though it was being generated like a voltage source. And we do this, right, for a battery as well. If you think about it, a battery generates a voltage and has internal resistance, which is all part of this current generating process in the battery. But the equivalent, we can just take out that resistance and put it in series. And that's exactly what I've done here. So this is like the equivalent circuit to the battery. But now we've got this EMF that's being generated by this external field in the inductor. Right. So what I'm going to do, I'm going to analyze this now in terms of circuit theory. You do see these questions in prelims. To some extent, they're questions from hell, but they shouldn't be, because once you know what's going on and remember these words I'm telling you now. Good. So the question may be, calculate the self-inductance of this inductor. What is the current drawn in this resistor and its phase with respect to the phase of the current with respect to the EMF or something like that. So that's what I'm going to do now. So self-inductance of the coil. Self-inductance of the coil is whatever it was up there. L equals mu naught m squared over L A. Right. That's the self-inductance. So the back EMF induced due to L opposes the changing current. And that's, of course, Lenz's law. Therefore, Ohm's law, so we can write down Ohm's law in this case. For current flowing in the coil. Right. So here is the battery term, the voltage generation. So this is the induced EMF. And it's just like Ohm's law. Well, it is Ohm's law. IR, right? IR, so the voltage across the resistor plus the voltage across the inductor. And this is the back EMF. And I hope I've convinced you about that sign. Right. If I had the minus sign in there, the current would just take off in the circuit. It would just go off to infinity. So it's actually what we have a potential difference across the inductor, which is caused. Right. So it's opposing to that current. It's opposing the flow of current. Right. Hence the plus for opposing it. Good. Whoops. So now I'm going to go to circuit theory. So alternatively, we can write I hope this sort of notation has been used. Who lectures this? Who lectures the circuit theory these days? Is it Todd? Somebody called Todd? No.
No, it was the conspiracy lecturer.
Nobody knows. Sorry?
It was previous lecturer, I think.
Oh, right, okay. All right, well, if that's V equals IR, right? That's just, the voltage is current times impedance. And all these are complex. Where Z is the complex impedance, you must have come across that. Z, the impedance I can write as the magnitude, where phi is the phase between current. Whoops. Now, I just don't know if this is the notation you use, but what the hell, I'm going to crack on anyway. The EMF, or the voltage that's driving this circuit, is the real part of epsilon naught EJ omega t. You will have used that, where epsilon naught is equal to NA omega B naught. Right, now I have to pause to think there. Somewhere it came up here. NAWB naught, it's somewhere here. NAB, it's gone off the top of the board. Are you happy with that? Do you want me to pull the board down? Oh, right, okay. Yeah, all right. It's just a phase difference. Yeah, thanks. But I can, all right, if it'll make you happy. Here we are. Yes, I'll take the imaginary part. That's absolutely fine. I can do that because it's a sine. Right, I'll take the imaginary part. That's great. It doesn't matter if I take the real part or the imaginary part. It is just a phase difference. Right, good. But you're right to point that out. So that's epsilon naught. So the current, so I have to now be consistent. The current, I have to take the imaginary part here to be consistent. Sorry, its current is I naught. The imaginary part of EJ omega t minus phi. Right. So that's the voltage generation. That's the current. Where what's that? I0. I0 is just equal to epsilon naught over the magnitude of Z, which equals epsilon naught over R squared plus omega squared L squared. Right. So that is the current. That's the magnitude of the current. It's all from circuit theory, right? And so that's the magnitude of the current. That's the magnitude of the current. That's the magnitude of the voltage there, i.e. the back EMF. And the phase angle phi is given by tangent of the imaginary part of the impedance to the real part. And that is just wrong. Tan phi is the imaginary Z over real Z is equal to omega L over R. There. Good. So is that clear? Right. Now that's just a bit of circuit theory thrown in. The important part is the calculation of the self-inductance and what happens, this equivalent circuit, and what happens to the current flow. Now, I think I'll I'll go for this. It's a very short derivation. It's another example. It's the self-inductance of a coaxial cable. So, or the self-inductance of two concentric cylinders. So this is A, that's B. That's just the geometry. So Ampere's law for in that gap, A less than or equal to R less than or equal to B. Right, now this is the... Right, so here we have, that is the direction of the field, right? It's radial, looking head on. It's azimuthal. It goes round and round. Okay, as in the picture here. That's it. It's like that. So the B field, we derived this before, mu naught I over 2 pi r. And if you don't believe me, then just recall how we did it. We did an integral b dot dl is mu I naught, I, and here is the field. The circumference is 2 pi r. Which gets me that. So it was a really simple calculation. All right, using Ampere's law, circuital law. So note, this is important. Linking flux. This is radial. Now, this is a common mistake in this calculation. The field is going azimuthal. It's going like round inside here. So the flux isn't, the area for the flux is not the area of this annulus here, because that's linking no flux. That's parallel to the flux. The surface linking the flux is radial, like that. Okay? It's a different shape. And the magnetic flux is given by phi, so I have to integrate from A to B, L mu naught I over 2 pi r dr. Right, so this is length L here, some length L. So this is the field changes in this gap, so I have to integrate from A to B of this area here, which has length L and a thickness dr, because I'm integrating, right? So I'm integrating from A to B. dr is it's sort of like an element of area. dr times L, right? It's the element of area inside there, and I'm integrating over the whole surface. So if I do that, phi is mu naught I over 2 pi log E B over A times L. And so the inductance is phi over I is equal to mu naught over 2 pi log E B over A times L. And that is the self-inductance of a coaxial cable, which is the same as the self-inductance of concentric cylinders. Right, so that's it. That's me out of here. And see you on Monday. Thanks.